Hello, everyone. So happy that you are all coming here so early in the morning. I understand that it's 9 a.m. over there. It's 9 p.m. Where I am, so a bit of a time difference, but shouldn't be a problem. Unfortunately, I can't see any one of you while I'm looking at my screen, but I'll pretend that you're there. I'm Nick Mulleners. I'm a PhD candidate from Utrecht University, working with Johan Jeuring and Bastiaan Here. And I will present my work on program synthesis using example propagation. All right, first of all, what is program synthesis? I've given a small illustration of what program synthesis should be. We have a specification, and from that specification, we want to generate a program that adheres to that specification. And we can see this as a sort of a search problem. This visual represents a tree of possible program candidates from which we want to find one possible solution that adheres to the specification that we gave. But for now, I won't look too much at this search space, this program tree. Just look at the specification and the program that comes along with it. So what you might think of a specification is, for example, for the solving a quadratic formula. Let's say we have the formula ax squared plus bx plus c, and we want it to be equal to 0. We could try to generate a program that has a, b, and c as its input, and the possible values of x as its output, and then a correct program that we would hope to synthesize would be the famous ABC formula. Now we can see this as a sort of a program by substituting in the values of A, B, and C, and then doing some normalization steps to come to the answer. Yeah, this is more like a mathematical ideal. I am specifically looking at program synthesis for functional programming languages, statically typed functional programming languages. And in particular, I will be using some syntax from Haskell, but it could work for many functional programming languages. So let's look at the function refers, which is a common function in Haskell that takes a list and basically swaps around the order of the elements. Now, giving a specification for refers can be a bit more tricky. You have to show that the lengths of the input list and the output list are the same, and you have to do something with the indexes. It's a bit easier to just give an informal or incomplete specification, such as this one. I use this notation to represent input-output examples, where here the input empty list is mapped to the empty list, and the input list 1 to 3 is mapped to the output list 3 to 1. Now, this is an incomplete specification, which is not ideal, because maybe our synthesizer would generate a program such as the following. The map function, which maps a function over a list, applied to the function that subtracts its input from the number 4. And you could easily tell that this is a correct implementation for the specification that we gave, but it's not a correct implementation for reverse. But this is just how incomplete specifications work. You can always overfit your specification. And I'm going to try to argue a bit why this is not necessarily a bad thing, right? Because the above specification for solve and similar specifications that you could write for reverse are relatively tricky to write. You could argue that they are actually a different paradigm from the programming language wherein you are trying to program something. So the reverse function in Haskell is fairly simple to write, but the specification for the reverse function is much more difficult to write. And a practical program synthesizer would actually allow the programmer to get their result, the reverse function, doing less work than they would do when they write it themselves, right? That would be nice. Test-driven development is a thing, definitely in functional programming as well. So in a sense, using input-output examples as a specification for a program synthesizer is the same as saying to a programmer, first write your tests to test your development, and then maybe the program already follows from that. But in this case, the specification wasn't very good, so the outcome is also not very good. Yeah, you get what you deserve for writing such a bad test, I would guess. In this case, the problem also lies a bit in the fact that that we expect the values in refers to be integers, but it might as well be something of any type. And in Haskell, we represent it using a type. We could say for all A, we have a list of A as input and a list of A as output. As such, it shouldn't be possible for the synthesizer to synthesize a program that uses the value 4, because we are working with polymorphic types and not with integers. And we can see the type as another kind of specification along with the input-output examples. And this specification, these two specifications together, are strong enough to give a correct implementation of reverse. Now, the exact implementation I'm showing here is not that relevant, but it's a write fold over a list, which basically says for the empty list, we just return the empty list, and for the non-empty list, we recurse on the tail of the list, and then append the head of the list at the end, and then this together reverses the list. But interesting here is that we use some different functions to define our reverse function, right? We use map, fold R, and the append function ++. And these different functions seemingly come from nowhere, and they have a big influence on the behavior of the program or what programs are being synthesized. Another example that I haven't shown is that you could also implement reverse using a left fold, which gives a better implementation, because those who are a bit more versed in Haskell will notice that this right fold implementation is very slow. It's not very efficient. But to illustrate a bit more what these different different kinds of functions, how they influence the program synthesis, I will introduce the running example, namely the dupli function. The dupli function takes a list and duplicates each element in the list, creating a list that's twice the length. And here we have a specification that takes the empty list to the empty list, the list containing A to the list containing A twice, and then the list A comma B to AABB. Now, sort of the first implementation that you might learn learning to program Haskell is the following, where you simply pattern match on the input list and then do a structural recursion on the tail of the list. And yeah, this is a good implementation, but you could also have, for example, the following, where we again use a write fold to implement it. And these two definitions are basically equivalent. Only one uses a recursion scheme. But there's other ways that you can implement the dupli function that are different in nature. For example, you could use the map function to turn each element in the list into a nested list containing that element twice, as shown here using map. And then we can concat this list of lists together so that we get one list again. And this is the same function. It's also correct, just uses some different functions as input. And there's many more ways to implement dupli, just using like the base library. Interestingly, the most terse one is perhaps this one, where we use the monadic bind operator to bind the list into the function replicate. Replicate takes a natural number and a value, and then repeats that value that many times to create a list. And this may be the most terse version of dupli, but not necessarily the nicest one. And so you can see how the different functions that are in scope can influence the what kind of functions would be synthesized, or what possible implementations of a function there are. I've also highlighted this recursive call to dupli here, not because it's a different function in scope, but it's sort of a design choice to whether you want to allow structural recursion or not. Now, there's different kinds of synthesizers that use input-output examples, as I've shown, and types to implement functions. So, for example, there's myth implemented by Ozera and Stancevic, and then extended by Frankel et al., which uses structural recursion to basically implement the first definition of dupli that I'm showing. And then there's an extension introduced by Lubin et al. Called Smith, which adds some extra features. Interestingly, this specification here is technically not strong enough for myth to synthesize the function dupli, but it is strong enough for Smith. So there are some slight differences there. But in general, they use the same principle. And then there's, for example, the synthesizer lambda squared by Faeser et al. That would implement this function using fold R. Now, technically, lambda squared could also implement dupli using a left fold, but yeah, I haven't shown that one in the slides. But in general, lambda squared uses recursion schemes or catamorphisms to implement functions. But neither of them is able to implement the functions below. And this is where our new synthesizer called Scribe comes in. Scribe is able to implement all these different functions given the right context. Though I have to add the asterisk there. Scribe is would technically be able to implement the structural recursion one, but we have not allowed structural recursion in Scribe because we're focusing on adding having extra functions, having a greater context of functions to use. We're not really focusing on structural recursion, but there's no technical difficulties there that would be have to be overcome. And another note is that the fold R function and the monadic bind in Haskell, technically they are implemented as part of type classes, which we don't implement. But if we would have the version that is specified for lists, then we could implement all these different functions. So to give an overview of Scribe, we take a type, which we hope the programmer would already provide anyways by type-driven development. And then we have some tests, and similarly, test-driven development says that you should already have some tests available. Another kind of input that we haven't talked about yet are sketches. So often programmers will sort of program in a top-down way and start implementing a program, but leaving some parts unimplemented. So here we've described that with a square box that we will call a whole. And this represents part of the program that is not finished yet, but a sketch allows the programmer to show their intention by starting starting to program in a top-down manner. And many synthesizers use these different inputs. But what we haven't seen as much is that the context is used as a specific input that the programmer can provide. And usually the programmer would provide such a context, maybe by specifying specific imports or partly in their head by thinking about how they would implement the program. And this can be seen as sort of the jewel of a sketch where it's not top-down development, but it's more the bottom-up development of a program where you think about which parts you would need. Now, all these things that I'm describing are sort of inputs that you can give to the program synthesizer that generally are already available while the programmer is writing a program. So in a sense, if you use these inputs, the program synthesis is really a tool that helps the programmer, tells them first give me a type, first give me a test, maybe a sketch, maybe some context. And then before you actually start writing the program itself, it might already give you a valid solution. Now, in order to explain why or how this works, how Scribe is implemented, I have to admit that I lied a little bit before, because the synthesizers that I talked about, lambda squared, myth, and Smith, I said that they were not able to implement all the different definitions of dupli that I showed, but that's not exactly true. They are actually able to synthesize most of those, maybe even all of them, but it's just because dupli is a very small program. Because how these synthesizers all work under the hood is that they take the input-output examples and try to sort of propagate them through the program using example propagation. So they use the input-output examples to prune the search space. But at some point, this is no longer feasible, and then they all revert back to a simple enumerative search for the programs. And during this enumerative search, they will eventually find the programs that I described. But this only works because the examples I gave were very small. For larger programs, this enumerative search would not work. But now I will talk about this example propagation that I hinted towards. Sorry, forgot to show. This would be the implementation that Scribe would give for this context type, sketch and tests. So okay, now to the second part of the presentation, program synthesis using example propagation. Here I've sort of visualized again how example propagation would work. You have the program space in black, and in gray you sort of see how the specification would flow through all these possible programs. And at certain points, there are more programs, but the specification cannot be pushed further. In a sense, it prunes the search space by only allowing programs that do not have that are not contradictory according to the specification. For some people, this may help this visualization, but I will give a more concrete example now. So let's go back to our running example, dupli, and first look at just types, because type propagation is a good way to introduce example propagation afterwards. So dupli has a type list of A to list of A, and we might have a context with map, concat map, replicate, and repeat in scope. Map we've already seen. Concat map combines concat and map, so it maps a function over a list and then concatenates the result so that it's only a single list. Replicate, also talked about before. And repeat is a bit different. It's sort of replicate for an infinite natural number. So it will take some values in input and then return the infinite list containing only that value. So to see how the program space would build up, we're going to look at the hole we have here, the square box, and see that if we would introduce map here with one argument, then we can propagate the type through map and see that we go from list of A to list of A to our new type A to A, which fits nicely with the type we've seen for map. So this sort of tells us that map is still a correct program so far. We could look further at the different ways to implement this whole, but we'll look first at the other functions. So replicate here with one argument does not fit because it does not have the right type. Same for repeat, but concat map has the right type, and it introduces a new whole of type A to list of A. Now, there's many more programs that don't have the right type, so like all the natural numbers. But yeah, they're not super interesting for now. Now to fill the hole introduced by concat map, there's again a few options. replicate and repeat are now correct implementations or correct hole fillings. But map is not possible here because we don't have a list as the input for the hole here. And also another call to concat map would also not work, for example. Now we have, again, one new hole for replicate that we might want to fill. And here we just input any natural number. And no function can return a natural number in this context. So this is the entire program space. And as you can see, using this type propagation, we've been able to prune quite a bit of programs that were not type correct. But now we will do sort of the same procedure using input-output examples. And we start again from a single hole, but now we assume that we've already pruned the search space so that there's only type correct programs. Well, first we have map, which was correct before. In this step is no longer correct because map maps lists to a new list of the same length. But our input-output examples clearly show that the length of the list is doubled each time. So we cannot refine with map. We can, however, use concat map, and we get a very nice new specification for the hole, namely that A is mapped to A, A, and B is mapped to B, B. Now we have the two options, replicate and repeat, that were left over from the type propagation. But repeat does not work since it returns a list of infinite length and not of length 2. But replicate does work, and we get a new hole whose constraint is simply 2. So we need to know that it has to be 2, and we can see that in the possible refinements, the only natural number that would work is 2. Yeah, so this is the sort of way that examples can be propagated through a program. And yeah, I won't go very much into the way that this works, but I mentioned before the synthesizer Smith, which allows you to propagate examples, input-output examples through the sketch. So that global input-output examples, so it's like the one here at the top, can be propagated through a sketch. Well, we can sort of repeat this. We can sort of interpret each new hole that we introduce as a new synthesis problem and introduce the hole fillings as sketches. And by repeating this, we can propagate our examples through many different functions. And that's basically how Scribe works. So again, for an overview, we start with some imports, some type, maybe a sketch, and some tests. And yeah, we take all this stuff and we add some extra stuff to it. First of all, we by introducing all these different functions in the context, we might introduce many programs that are not in normal form. So, for example, if we introduce map and then the second argument is map again, then these could be fused together using map fusion, and we want to avoid these different programs that can be normalized to the same program. So we only want to generate normalized programs, and for that we use a technique similar to program sketching, program synthesis using equivalence reduction, as introduced by Smith and Albarguti. And furthermore, we can add weights to the context, so the different functions that are in scope, we can give them some weight, and then this means that some program paths will be explored earlier in the search, allowing us to get some more control over what programs will be synthesized. And with all this together, Scribe is able to give a solution like this one. All right. That was my presentation. I hope you enjoy it and that you have some good questions.
All right, let's give Nika a round of applause. Where are we at on?
Okay, so do you want to invite the room of people other than me to the stage?
Okay.
Okay, so we can have questions from the room, and oh yeah, maybe
I just go to
right. We can carry the mic to people in the room. Okay, we have one question from the room, and if there are questions online, you can type a question in the Q&A. But we're also bringing people to the stage, so you'll be able to speak as well.
Is there a trick to turning this on?
Okay.
There it goes.
I think it's on.
So near the end of the presentation, when you were pruning the set space, there were some statements made like, this is going to return a list of the same length so we can prune this branch, or this is going to return an infinite list so we can prune that branch. Are we assuming that the library, like the things we've input, have some additional specifications that the solver has access to in this in Scribe?
Sorry, I couldn't hear the last sentences, I think.
Okay. Are we assuming that under the hood, these methods have, so these functions have some specifications beyond just the type, so it can prune those paths, or was that just kind of like hiding the fact that maybe it's actually just executing the test?
Okay, so if I understand correctly, you're asking if each of those functions that are used during the synthesis, if they have some specification that allows these examples to be pushed through like that.
Yes.
And the answer is not really. All the functions are simply defined over algebraic data types using either structural recursion or recursion schemes. And the way that these examples are pushed through is by using live bidirectional evaluation, which is introduced by Smith. I decided not to go too much into that during this talk, but what it boils down to roughly is that the functions are evaluated as far as possible so that you get some sort of result that might still contain holes. And all the language constructs that are left over, they are fairly simple. They're like pattern matches and maybe one recursive call and some constructors. And pushing examples through that is way easier. So it basically happens by evaluation. And then there are some caveats that means that not all functions would be supported. But for most of them, it works well.
Okay, that makes sense. Thanks.
Thank you for the question.
Well, people in the chat can raise their hand.
Okay, so Michael had a question, but Michael, you're on the stage now. Do you want to try to ask verbally?
Yeah, can you hear me now?
Yes, we can hear you.
Yes.
Okay, great. Thanks, great talk. Enjoyed it. Thanks. I'm wondering how the synthesis algorithm uses the constraints in a way that doesn't result in generating and then having to reject lots and lots of programs.
Yes. So generating the constraint is sometimes a bit of a bottleneck, right? It's also explained in a paper a bit. There's quite a bit of overhead sometimes in generating these constraints, and then if we only throw them away to prune the search tree, is not very useful. But the constraints are also used as a heuristic during the search. So if a constraint is very large and it seems like it's not going to be resolved quickly, then we use the weights to assign more weight to that search path, so that other programs are tried earlier. Yeah, hope that makes sense.
I guess what I'm thinking is, the synthesizer generates a bunch of programs, and then some of them are incompatible with the hints or constraints that have been generated so far. So you've got to reject those. Do you have to actually generate all these programs and then reject them, or how do you? I mean, the point of this is that you want to avoid exploring. You want to prune the tree, right? So how are you able to prune the tree early enough Is it just that you prune the tree with you prune nodes in the tree that still have holes in them?
Yes, yes, exactly. So
Okay.
every time you introduce new programs are generated one step at a time. So every time one hole is just filled with one new expression that might contain holes, and immediately constraints are propagated through, if possible. And so the first time, at the moment that this is no longer possible, that like a map is introduced that does not map the same value to the same outputs, for example, then this whole part of the tree is pruned. So the hope is that the time that is spent in propagating these examples will be gained back by being able to prune away large swaths of programs. And the evaluation seems to point to that it is beneficial.
Okay, thank you.
Okay, so let's get the next speaker to get set up on AirMeet, and then while that happens, I'll just read out a chat Q&A question.
Alcides is online now.
Okay.
Do you want to unmute Alcides?
Yeah.
Yeah, sure. Yeah, it's working. Sorry, problems with the microphone. So my question was regarding the weights, whether you could elaborate a little bit on maybe the user interface for defining weights. I would assume that in different holes, I would want to give different weights to different functions. And related to that, how this maybe could be learned in the future.
Okay, he's on the stage now.
So currently there is not a very nice way for programmers to specify exact weights for the functions that are in scope. So to sort of simulate that, the weights are computed automatically based on how complex the type is of the function and how many new lambdas it will introduce, stuff like that. We weren't exactly sure yet what we thought the best way would be to allow the programmer to specify these weights. So for now, they are generated by us.
Thank you. Nice work.
Thank you. That's the question.
Okay, let's give Nick one more round of applause, and then